Alright, so I don't know, I just wanted to help students with projectile type problems, and specifically when you're on level ground, finding the range of a projectile. So on a prior screencast, I talked about this two-dimensional displacement vector, delta r, and how delta r is going to be your initial velocity times time and added to 1/2 at squared. And if you recall, this comes from the area of a velocity graph, but now this is in 2 dimensions. So this is 2-dimensional displacement. And this works when your acceleration is down due to gravity, and your initial velocity could be at any angle you want. So if you imagine, like, here's the ground, right? And you launch a projectile. Here's the path of the projectile, roughly. I'm just estimating what it might look like. Okay? So this vector here would be your initial velocity vector. I could draw that a little bit better. Let me try to draw that nicer. This vector here, that's still sloppy. There, nope. Right there. Haha. There we go. Finally. It should be a little longer. There we go. So that's it. And that's basically this vector. This isn't just my initial velocity. That's my initial velocity times the time the projectile is in the air. See, this is a vector equation. So I'm adding these two vectors to get that displacement vector. And my 1/2 at squared vector obviously has to be in the direction of my acceleration, which is down. So this is my 1/2 at squared vector. And this right here would be my displacement, or delta r. And in this rare case where you're on level ground, delta r and delta x are going to be the same thing. Okay? So I'm going to go to the second page, add a page. And so starting with that picture, if I work out my vector equations, of course I have delta r equals v naught t plus 1/2 at squared. Now I also have an equation for sine theta based on that diagram you just saw. So sine theta is going to be 1/2 a t squared over v naught t. Now I've dropped the vectors, and now I'm talking about the magnitudes of vectors now. Okay? So this is a vector equation, but now I'm just talking about the relationships between the sides of that right triangle you saw on page 1. Okay? So cosine theta is going to be delta x, the length of that vector, divided by v naught t, right? So what I can do now is using this relationship here, right? I could say that, let's see, I could say v naught t sine theta, right, has to equal 1/2 at squared. Now with this one, I can say v naught t cosine theta equals delta x, and then I can solve for t. So my strategy of why I'm doing this, you'll see in a minute. So t is delta x over v naught cosine theta, right? So my plan is to take that time and plug it in here and plug it in right there. Okay? So when the dust settles, right, I've got, if I can do this right, I've got v naught, I'll just copy down. Now in place of t, I'm going to put delta x over, I should do that in a different color. Hold on, let me go back. It'll look better. I'll use white. So I got v naught, and then I'll put t there, and then sine theta, I'll just rewrite that, equals 1/2 a, and then I'll write t twice, right? So I'll put delta x over v naught cosine theta, and here I'll put delta x over v naught cosine theta, delta x over v naught cosine theta. Okay? And after the dust settles, I cancel things out. I multiply both sides by v naught cosine theta, and these two are gone. I divide both sides by delta x, and this one would be gone, right? Because they'd be dividing or multiplying into one. They'd be dividing into themselves. Let's just clean this up now. I have v naught sine theta equals 1/2 a delta x over v naught cosine theta, right? So I'm going to have to go to the next page. That should look good so far. Okay. So next, and I'll just rewrite that to make it easy. I got v naught sine theta equals 1/2 a delta x over v naught cosine theta, right? So let's just solve for delta x. After all, that's the range of a projectile. So my whole goal with this is to find what's called the range of a projectile. That's the horizontal distance on let's say a horizontal surface. And this is easier than if you're like launching something off of a cliff or launching something down from a cliff. I'm just talking about launching something like a football player throwing a pass to his wide receiver. Horizontal surface. So that's what I'm talking about here. And what I want to do is be able to find the range for like any angle. So that was the goal I set out to do in the beginning here. And well, if I just rearrange things, right, solving for delta x, I should have, well, let's see, 2 is all the things that are in the denominator. This is in the denominator, that's in the denominator. So that's all going to move to the numerator on the left side, right? So I've got 2 initial velocity squared, right? Hopefully I'm not forgetting anything. Yeah, I got initial velocity times initial velocity. And then I got sine theta cosine theta. So that looks good. And that should be equal to delta x. And I forgot to divide by both sides by acceleration, which, by the way, acceleration is g, because it's due to gravity, right? And then you would want to remember there's a double angle formula that you got to know for this. I'll show you that in a minute. Let me just rearrange things a little bit. So if I rearrange it, I got v naught squared times 2 sine theta cosine theta over g equals my range. Okay? Now, this part of the equation here is a double angle, trig identity. If you don't know that, I'll write it down here just to remind you. I wouldn't have known. I have to look these things up too. So there's a double angle trig identity. And it looks like this. When you have 2 sine theta cosine theta, you can simplify that to sine 2 theta. It's called a double angle identity. See, you can see why, because you're doubling the angle. Okay, so I'm just going to put that, I'm going to use double angle right there to simplify this relationship. And when I'm done, when all is said and done, right, what I had was, let's see, v naught squared 2 sine theta cosine theta, right? That was over acceleration due to gravity. is my range. Now, replacing with double angle right there, what I ends up with is, see, range of a projectile. Pretty cute how this simplifies for any angle. That's amazing. It's so simple. Range is equal to, let's see, this stays the same, right? And this becomes, here I'll make it blue so it highlights it. It becomes sine, that looks lousy, I'll fix that, sine 2 theta, right, over g. So that's what I wanted to show you. Hope you enjoyed it. It's pretty cute and it's nice and simple. So if I plug in my initial velocity, I take the sine of twice the angle I'm launching at, and this is an angle measured from horizontal, divided by the acceleration of gravity, that will get me the range of a projectile. Pretty amazing. Hope you like it. Have a good day.